This is going to be a worked example on how to graph either a tangent or a cotangent function. The general idea behind both of them is pretty similar. One of the biggest differences is that in the cotangent, you kind of drop this pi over to omega term when you're calculating the phase shift, but the general idea behind both is the exact same. So we're going to be doing a tangent function just so we know how to handle that extra phase shift case. But anyway, so it'll start off how we usually do with our trig functions. We want to calculate period, phase shift, and amplitude. I spelled period wrong. Okay, there we go. So the period is pi over omega, but omega in our case is 1, so it's just pi. The phase shift, well, phi is negative pi over 3, and omega is 1, so I have a negative pi over 3, and then we're subtracting the pi over, well, omega is just 1, so it's pi over 2. And then if I calculate this further, pi over 3 turns positive, minus pi over 2. And then I can multiply, well, I can convert to a common denominator, so this will be 2 pi over 6 minus 3 pi over 6, and that equals negative pi over 6. Okay, so now let me make a little bit of room by removing my scratch work. Our phase shift is negative pi over 6, and then amplitude and baseline are just the standard values. And so similar to what we did with sine and cosine, well, I know my starting point for the fundamental cycle of tangent starts at my phase shift, and then if I add one period, that's my ending point. So my starting point is kind of negative pi over 6. Well, let me put it this way. Let me draw the axes, actually. Let's draw our axes. And, okay. So I have this negative pi over 6 term here, and I'm going to add an entire period worth of distance to the graph. And that's going to be at negative pi over 6 plus pi, but I can convert that to 6 pi over 6, and that simplifies to 5 pi over 6. So, and I'm trying to keep it relatively even. My axes might be a little difficult here, but I'll call that about 5 pi over 6. And then we can use the same idea as before in that the points of interest happen at the 1/4 marks throughout the graph. And so I'm going to try and fill that in. And what's a little tricky about this one, and it's kind of confusing, the 1/4 mark does actually occur a little bit after the y-axis. So that's something to be careful about, and we're gonna find out the justification behind that as soon as we start doing our calculations. And this gets a little convoluted, I won't lie, but again, I want to find out those tick marks. So my first calculation, well, sorry, before I even do that, I'm moving by 1/4 of the period, so I can take the period over 4. So we're moving by pi over 4 every single time we move on a tick mark. So my first calculation is negative pi over 6 plus pi over 4. I can convert these to common denominators. This will be negative 4 pi over 24 plus 6 pi over 24, and that equals negative 2 pi over 24, or sorry, positive 2 pi over 24, which simplifies to pi over 12. And because these numbers are getting ugly, I want to check that I'm right. Okay, I am correct. This is pi over 12. And now I am going to erase my scratch work. Okay. Next, let's take pi over 12. And to that, I can add another pi over 4, because we're going from this point to this point. And so, okay. I can convert 4 to a denominator of 12 by multiplying by 3 over 3. So I have pi over 12 plus 3 pi over, or sorry, not 3, over 12. And that equals 4 pi over 12. And that will simplify to pi over 3. So I put pi over 3 right here. And yes, that is correct. Okay. Finally, our last calculation. Again, I want to add one more instance of pi over 4. And now that I'm looking at it, I think this tick mark could be adjusted a little bit. Let's put that right there. Anyway, okay, it's pi over 3 plus pi over 4. Let's again convert these. 4 pi over 12 plus 3 pi over 12. And that's going to get us 4, 5, 6, 7 pi over 12. And I don't think we can really simplify that, so we'll leave that as 7 pi over 12. And then we also want to include some tick marks for -1 and +1. Okay, now that we have our axes all labeled, we can start drawing tangent. So the properties you want to keep in mind for tangent, and I have this on my worksheet somewhere. I want to make sure I'm using the correct language. Where is it? Where is it? Okay, so tangent at the very start of its cycle has an asymptote. So the start of my cycle, which is where pi over 6 is, I will draw, excuse me, I will draw an asymptote. Okay. Next, what do I say? It's also increasing. So if you know what tangent looks like, it's going to kind of make this general shape. Again, that's very inaccurate, but it is increasing always. The first point of interest happens at -1. And again, that's 1/4 tick along the graph. So at my first tick mark here at pi over 12, I have a point at -1. It's my first point of interest. Next, it has a 0, so that happens at my midpoint of interest. So there's a 0 right here. And then finally, there's a +1 at the third point of interest. And then it ends in an asymptote. So my last, kind of where the period ends, I can put another asymptote. And now finally, I can fill this in, well, I can try to, by drawing an increasing function. That looks kind of horrible. Let me see if I can do that a little better. Okay. My axes, my human hand is not great at drawing computer graphs, but generally speaking, you will get a tangent function here. Maybe I should move my, can I zoom out on, oh, I can. All right, here, let's try this. Let me give myself more room. I think you get, hopefully you get the idea. But it will look something like that, despite the fact that I did miss my graph a little bit. But besides my inability to graph functions well, what you really want to pay attention to is the fact that we were able to reuse that idea of 1/4 tick marks to label our points of interest. So tangent, again, sort of similar to sine and cosine in that we were using this 1/4 method to kind of put down the points of interest. And then if you were doing cotangent instead, you would use a slightly different phase shift formula, and you would get a very similar looking function, but it would be negative instead. It looks like tangent kind of flipped over on itself. But anyway, graphing tangent could be a little scary, but it's not too bad once you get into it. But anyway, that is a worked example on how to graph either tangent or cotangent functions.